So neurons are specialized for communication because of their structure. So there's quite a structure-function relationship here, right? There are multiple inputs to dendrites. Some of these are going to be excitatory, and they're going to push the neuron in the direction of firing, an electrical message, which we refer to, and we'll learn about this week, as an action potential, right? And other kinds of inputs that are coming in at those dendrites, right, are going to discourage the firing, of an action potential. They're going to be inhibitory kinds of messages. So lots and lots of messages coming in, some excitatory, some inhibitory. Remember, up to 10,000 distinct connections onto a single neuron, especially one that was raised in an enriched environment with lots of spines. Well, the cell body is going to help to sort of integrate all those messages. We're going to see that excitatory inputs result in the entry of specific ions, and inhibitory, messages will actually result in the influx of other ions, and there's going to be a balancing done, a summation sort of done, and integration done at the level of the cell body, and then especially at the very beginning of the axon, where there's a bulge, where it's a little hill at the start of the axon. It's called the axon hillock. And there are going to be specialized machines there that are going to be specialized kinds of channels that are going to determine at that point, make some sort of a determination about whether a message should be sent, an electrical message should leave, and head down that axon or not. We'll be talking about this, so don't panic yet. I do want to point out right at the start here that the message that's going to travel within a neuron, that's going to go from one end to the other, is electrical in nature. Okay, and axons are, you can sort of think of them as the wires, basically that are linking, sometimes very disparate regions of the nervous system. And I write here, the neuron is like a computer chip, but that's a terrible analogy, and I'll tell you why. It is like a computer chip in the sense that, a computer chip has a certain set of inputs, excitatory, inhibitory, and then generates a particular output based upon those inputs. That's what a computer chip does. I mean, the electricity flows along specific pathways depending on the kinds of inputs, right? Well, that's true about your neurons as well. However, the most remarkable thing about your neurons is that these are biological machines. These are biological computers, biological integrators, right? So the critical thing to keep in mind is that a biological machine can actually physically adjust or change its structure based upon the kind of input that it's receiving, so that the next time input comes through, it might operate very differently. It may have actually physically altered the pattern of connectivity, the strength of individual connections, and the specific kind of situation or conditions required to generate an output. So it is a computer chip in that sense that it integrates information and then produces a specific output, but it is different, very different, in that it is flexible and responsive to environmental cues, to experience, and it alters its structure and thus its function, based upon that experience.